I'd asked you to do was go down through the hydrocarbon column and tick or X. So hydrocarbon has to have a C and a H only in its formula. So water is not a hydrocarbon. These are because they only have 5 C's and 12 H's. The alcohol down here cannot be because it's got an OH group. Pentane, if you Googled it and got a formula, would have been pent is 5 is C5H12. So it's these two are the same. That is an alkane. Here, there's only C's and H's. There's only C's and H's. The fact that you have the nitrogen in the bottom one, that changes it. It's no longer a hydrocarbon. It's a different homologous series in there. So today we are going to learn about our first family, figure out its structure, and I use these two stupid sentences to help me out in terms of having to write formulas for hydrocarbons. So monkeys eat purple bananas and pigs hate hot oatmeal. It's going on, it's the bottom of page 161 in your book. So the families that we are going to do in our fuels section are alkanes, alkenes, alkynes, and we're going to talk about aromatics. So we said that on Friday. So the order for naming, it's like chemists, how do chemists count carbons? They use this, the monkeys eat purple bananas and pigs hate hot oatmeal. This is how you count. So the M stands for meth, and you give something the name meth if there's one carbon in it. 2 is eth, if it is 2. 3 is prop. 4 is bute. So if I have a compound and it has 4 carbons, it's going to have bute in the beginning of its name, and then I've got to figure out what's the homologous series. So today we're going to do the alkanes. Alkanes and end in ane, so a bute would be a butane, is what we're going to learn today. Then we go to 5 carbons is pent, 6 is hex, 7 is hept, and 8 is oct. Now, in terms of our different homologous series, you need to know the most about the alkanes. So you will have to be able to name up to 8 alkanes. For everything else, I think it'll stop at pent, and then for some of them even we only do eths. So the most alkanes you will have to name will have to be up to 8. Okay, so, monkeys eat purple bananas, pigs hate hot oatmeal. The ones that probably give the most problem are the prop and the bute, in terms of remembering what's what. But if you can think pent is 5, hex is 6, that should be doable. Is there any questions on that? We okay? Okay, trying to see. So over the page you have a big long table. There are literally 8 boxes in it. Everything that we're going to do today ends in ANE, so that makes it easy in terms of the naming. So you need to write a name and a formula for the first 8. You need to figure out what is its geometry, and I'm going to help you out here and tell you have 2 choices. You have tetrahedral or you have planar, so you've got to figure out your carbons. So we're now using stuff that we did in Form 4 for this. And as I say, you should have your marshmallows, or some of my 4th years last week used grapes, which I thought was really clever. And you're going to see, can you do some making? Now, phones and taking photos of your work can actually be helpful for this particular thing, because then you have a little record of it. So you are going to make me probably C1 to C6, and it's going to probably be hard with marshmallows because they're not going to have the links that my Molly Mods would. You just put it on a piece of paper, You can do them all, you can do them one. You're probably not going to share them with me today other than to ask me questions, but you write down its name, you get its formula. So the C will always come first in the formula, the H will always come second, and you're counting them all up. You figure out is it tetrahedral or planar geometry, and you're going to draw your molecule. Okay, so this is one version of it with just a molymod and the H's around it. So this would be the first one, methane, CH4. I'm not going to tell you the geometry because you're going to tell me, but I'm going to show you my molymod. Okay, I'm going to put you somewhere where the sun isn't going to shine. Okay, is that marginally better? It's marginally better. So this is my molymod for methane. Black ball is carbon. It's got 4 bonds coming off it. Carbon will always have 4 bonds coming off it, so you always need to give a quick count around each carbon to make sure that that is the case. And if you won't be able to see it with your marshmallows because your marshmallows won't have the links on in the right place, but I have a hydrogen going up in the X direction. I have one in line with the Y, and there's one coming out to the front to you, and there's one coming out the back for me. And that's what, these are the 4 bond pairs getting as far away from each other as they possibly can. So you don't have to make 7 and 8 because the marshmallows you won't be able to lift it and move it. But can you write the blurb with that and the shape, name, formula, geometry, and structure? Okay, do you have any questions? Okay, so you'll have 4 things for each one. You can write them in your table. I'm going to give you 20 minutes. So I will stay here. It is 9:01, so 9:20. Come back to me if you want to turn off your cameras.
How do you figure out the bond angle?
So you should know from 4 bond pairs what the bond angle is. Obviously with marshmallows, Miles, you're not going to be doing that, but you should be able to figure out bond angle from 4 bond pairs. Okay, so if you want to turn off your cameras, I will be here.
Miss, which ones are we doing?
You're doing, you're making C1 to C6 with marshmallows or grapes or whatever the hell you have, and then you're only just going to write out 7 and 8, because I don't think your you might not have enough marshmallows. Maybe you will. I wouldn't have enough in my molymods for you to make 7 and 8. Mikey, does that answer your question? What was your question?
Well, like, what would the formula be?
So you have to make it. So if you're doing C, like if you do the first one and you make it, it's got 1 C and then it's going to have H4. And then you're going to make your second one. And you'll be able to work out, if you've made it correctly, what it's going to be. So every carbon, every black ball has to have 4 toothpicks coming out of it. So if you have ethane with 2 carbons, you would join that, and then you'd fill the rest of the spaces with hydrogen. Does that make sense? Okay, folks, we put back on cameras and we will have a look. You can tell me how successful marshmallows were. How do we get on? Thumbs up, thumbs down. Thumbs up. Feeling confident? Alrighty, so I've shown you methane. Here, 4 bond pairs. So what is the shape of something that is 4 bond pairs? Has to be tetrahedral. So number 2 in the bed should have been ethane. So you make sure each carbon has 4 lines coming from it. So therefore the formula for ethane has to be C2H6. Again, it is going to be tetrahedral in geometry. If you look around each carbon, there are 4 bond pairs. So that has to make it tetrahedral. This is one tetrahedral. This is the second. When you look at ethane, this is what it looks like. Okay, now what you probably can't get from your marshmallows is this single bond. It can rotate, and obviously we know that electrons will repel each other in the bond pairs and they will want to get as far away from each other as they can. So it may be in reality that it's actually clicked like this so that the bond pairs are as far away from each other as they can possibly get. But having a single bond in your molecule makes it flexible, so these bonds can actually rotate in 3D space. So after eth, we do propane, and again, if in doubt, draw it out. So you make your carbon chain and then you fill everything with H's, so that will make this C3H8, and again it's going to be tetrahedral in geometry. So this is what our prop looks like. So in reality it can go like this, but it won't want to do it because it'll want to get as far away from each other as it possibly can. So sorry, it won't do it with the prop, but they will rotate as far away from each other as they possibly can. They can rotate, so they will be off aligned in terms of their electron pairs, just so that they can get as far away from each other as they can in their fixed space. And you'll see when we do the bute, so bute 1, 2, 3, 4, fill everything with hydrogen. So if you omit even one hydrogen from a structure, so you just forget to put it in, you get 0 marks. And it does happen, so make sure you have checked and you have that you know for definite you filled all of your hydrogens. So after bute, so this is what butane looks like. So it could in reality go like this, where my 4 carbons are going boom, 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 but it won't. But it will try to get away as far away from each other as it possibly can. So it will never be an arrangement like this. They'll try to get away from each other as far away as they possibly can. So in terms of our bute, we go pent. 1, 2, 3, 4, 5, fill with hydrogen. So I'm going to get lazy now and not fill with hydrogen, but this should be C5H12, and again it will be tetrahedral in geometry. So here I'm just going to get rid of that one at the end, and we now have 6. 1, 2, 3, 4, 5, and 6. So as long as you have every bond filled with H's. So it's going to be hexane, and it is going to be C6H14. It will be tetrahedral in geometry, so all alkanes will have tetrahedral geometry. 1, 2, 3, 4, 5, 6, 2, 4, 6, and 7. So every time you are drawing these, you are putting in your H's. I occasionally get lazy, but I'm never going to be, SEC is never going to ask me to draw them, so I can afford to be. You cannot, so don't get into bad habits, is the moral of the story. And the last one then is going to be oct. 1, 2, 3, 4, 5, 6, 7, 8. So then this is octane. It'll be the biggest one you'll have to draw, and it's going to be C8H18. Okay, all tetrahedral in geometry. Now, do you have any questions on those, please? So we have just a couple of little questions in the bottom of page 163 and a little bit on the top of page 164. So if you want to have a read down through them. Okay, so if you're happy to go through, start going through the questions. Okay, so are alkanes hydrocarbons? Thumbs up or thumbs down? Thank you for my people that are audience participating. So yes, they are, and the reason why is that they contain carbon and hydrogen only. And that's the key thing. It is the only. Are they aliphatic or aromatic? So thumb up if you think they're aliphatic, thumb down if you think they're aromatic. Thank you, Foncha. Thank you, Eva. Thank you. Okay, they are aliphatic. So how do you know they're aliphatic? Anyone like to share? Oh, lads, don't all speak at once.
They don't have the benzene ring shape.
Okay, so then tell me, what do they have? What part of the aliphatic definition do they have? Because you're absolutely correct, Eva. There's no benzene ring there. But what do they have?
Straight or branched chains.
So the ones we've drawn, do they have any branches on them?
No.
Not yet. We will do branching on Wednesday. So the ones that we've drawn today, they are what are called straight chain molecules. They only have the carbons are all in a line. Okay, so C is in a line is the giveaway. When we have branches, there'll be a C popping off the main chain. So they are a homologous series because they're the same family. So yes to our homologous series. Which compounds are going to have the lowest melting points and boiling points? Of the ones you've drawn today. So you've drawn 8. Which one?
Octane.
Say it again.
Octane.
So octane is the biggest one. So we're going to start talking today a little bit about van der Waals. Octane will have buckets of van der Waals because it has a really high molecular mass. So it's going to have a really, really high boiling point. So things that have the lowest boiling point, they're going to be the smallest molecules. So it's going to be methane is going to have the lowest boiling point. And we'll explain the reasons for that in a second. Is anyone able to figure out what the general formula is? So instead of putting a number in your formula, you put an N to designate the number. It's not an easy thing to do. So alkanes all have the same general formula because they're the same homologous series. So N is for a number. So it is it is CnH2n plus 2. So if you look at something like ethane and you know it's got 2 carbons, then 2 2s are 4 plus 2 H6 is going to be its formula. So it's called a general formula. They can occasionally ask it, so it helps to know it from that perspective, but it also helps to know it from, do I have the right formula? Personally, I just like to draw out my compound, and I know that I have to fill it with hydrogen, and I work out my formula from that. But some of you may like the general formula to use that. Okay, I just want to show you these. This is just blurb. You don't need the blurb. It's more the diagram. So they're the simplest hydrocarbons. They're found in crude oil. They're made of carbon and hydrogen only. They are joined by what? By single covalent bonds. So the single covalent bonds is in the chain. That's what we're interested in. And there's this word that chemists use to describe it, and that is saturated. So explain the term saturation, and that is when a molecule is joined by single covalent bonds. When I worked in the UK and we were doing saturation, they don't get it, because if you say to them, oh my God, I'm saturated, they'll have no clue what you're talking about, but all Irish people do. So if I'm saturated, what's wrong with me?
You're wet.
I'm totally wet. So in a chemistry perspective, if something is saturated, it is full of hydrogen bonds, or it's full of hydrogen, and everything is single covalent bond. Okay, so that is saturation. And alkanes are saturated. Okay, so we've said each carbon has to have 4 bonds, and then there'll be 1 bond from hydrogen, and we've done these. And these are just showing you the different representations of methane. So this one here is going to be the one that you will be representing all of the time. This one here is just showing it to you in 3-dimensional space. So this is the one that's in your X direction. This is in your Y. This is coming out toward you, and this one is going away. So that's just showing you in 3-dimensional space. But this one over here is going to be the one that you will be vomiting up on paper for them. And this is obviously a 3D molly-mod at the very end, just to show you. Okay, so we need to talk a little bit about their physical properties. So why are C1 to C4 are gases? So this is the top of page 164. It didn't animate quite the way I wanted. And C5 and above are liquid. And the reason that is, now we're going back to intermolecular forces that we did last year. So there are 3 intermolecular forces. Van der Waals is one. Van der Waals. You have the dipole is your second. And the third is going to be hydrogen bonding. So each time you're looking at an organic molecule, you're looking to see what does it have. And the only thing that alkanes have are van der Waals. So if you were to use your electronegativity table and find the difference between C and H, you will find that it is 0.4 on the button. There's no delta positive, delta negative on it. The only intermolecular force, therefore, it has is this thing called van der Waals. And van der Waals works on the basis of the bigger you are, so that's this increasing molecular mass, the more electrons you have, the more van der Waals you have. Now, I've written it like this specifically to hit any version of a mark scheme that she can present to you. Okay, technically van der Waals has to do with how many electrons you have, but she has started to bring in molecular mass into her definitions, so writing it this way hits whatever she wants. So increasing molecular mass leads to increasing weaker van der Waals forces, as has more electrons, and then the bigger you are, the more van der Waals your molecules will be tied closer together. So once you get to C5, the force between molecules is so strong that now the molecules are liquid. Whereas C1 to C4, while they're attracted to each other, they're still able to be far apart. So all of our physical properties, melting point, boiling point, density, state of matter, all have to do with the IMF that's present. So you need to recognize when you look at a structure like this, what is the intermolecular forces that are present. So there's no hydrogen bonding because there's no nitrogen with hydrogen, there's no oxygen with hydrogen, there's no fluorine with hydrogen. There's no dipole because the mass makes it the 0.4. Okay, I think this now may disappear on me. So we'll just, hopefully it won't. Okay, do you have a question on that? Please ask if you have. Okay, we have two more things to go through. So boiling point, we looked at it when we looked at methane. The boiling point will increase with your number of carbons, and your boiling point again depends on your intermolecular forces. So this is going in your top section, and this is your reason. So again, alkanes only have the weaker van der Waals to overcome. The bigger the molecule, the more electrons and more van der Waals forces, and then you'll have a greater boiling point. So for the ones we did today, octane has the highest boiling point because it's the biggest molecule. It has the most electrons, it will have the most van der Waals. Highest boiling point. Now when we do all the other homologous series, we will be writing the same thing for physical and boiling point and even solubility for the ones that we do in Form 5. Because all they're going to have is going to be the van der Waals. And just to remind you, again, I am putting this descriptor of weaker in there to, again, hit any weird question she can ask. Because now you're just putting a degree of strength on our intermolecular forces. Okay, we have one more slide after this, and then we will leave it for this morning. Okay, I'm going off Eva and Fonch at the moment, so, and possibly Jill in terms of writing. The rest of you, I can't figure it out. So, we good, ladies?
Miss, the microphone thing is in the way.
Sorry.
The last bit for me.
Okay, it's, I think my, whatever it's called, has frozen. Oh, it's working back. That better?
Yeah.
Okay, so we're looking, when we talk about physical properties, we're looking at what's the intermolecular force. The only intermolecular force alkanes have is van der Waals. So that's going to influence not its chemical properties, but its physical. So Rachel, can I go forward?
Yeah.
Thank you. Okay, so when we talk about organic compounds, we talk about their solubility in water, so in polar molecules, and in organic solvent. So organic solvent is essentially non-polar, and water is polar because it can hydrogen bond. So last year we did hydrogen bonding. This is not the best diagram of hydrogen bonding that ever existed, but to hydrogen bond you need to have NOF present. A nitrogen with a hydrogen, an oxygen with a hydrogen, or a fluorine with a hydrogen. Methane does not have NOF. There is no nitrogen, oxygen, or fluorine in there. Therefore, it will not like water. So it's insoluble in water, and because it is non-polar, so this is a non-polar compound, this will be soluble in organic solvent. And the most common organic solvent that we will use in the lab is a thing called cyclohexane. And the reason now for our solubility is there's no hydrogen bonding possible, there's no nitrogen, oxygen or fluorine present, there are no dipoles, there is only the weaker van der Waals. Van der Waals.
So, Miss, what do you write in the top box?
So the top box, insoluble in water, and if you want to put polar in brackets, that's because water is a polar molecule, and it's insoluble in organics, or soluble in organic solvent, and organic solvent is non-polar. So methane and all the alkanes are non-polar. They have no dipoles, no difference in electronegativity. So cyclohexane is a non-polar solvent. So this is what you're putting in your box. Now we've done some this morning, the question 5 stuff that you possibly didn't like or didn't understand last year. You kind of now got to get your head around it a little bit. Okay, so just to remind you, in terms of figuring out dipoles, you use your electronegativities to do that. You take away the numbers that are in that electronegativity table, and if the number is greater than 0.4 and 1.7 and less, then that is a polar bond, and then we have to figure out what is the polarity of the molecule then. So we're using bits from last year. And when we do our electronegativity for C and H, when we do that piece of maths, we get 0.4. It is a non-polar molecule. Because I have 4 bond pairs in symmetry, it is a non-polar. Sorry, so the 0.4 makes it a non-polar bond, but the fact that it's got 4 bond pairs and it's symmetrical makes it a non-polar molecule. There's nothing in there to change the distribution. So 4 BPs, it's the same element. I think it's rule 1 from last year. It's a non-polar molecule. 4 bond pairs, same element, symmetrical, makes it a non-polar molecule. So your homework has pinged. It's really, really important now that if I asked you to draw octane, you would be able to draw it for yourself. Heptane, hexane, whatever it is, that you can draw them, because when I see you on Wednesday, we're going to start making what are called isomers. So making branches out of the carbons we have. But if you can't draw the beginnings, you're going to have a tough time. And seeing as you're not question orientated currently, as you would be in a classroom, then you need to make sure you're getting in touch if you have problems.
Miss, I have a question from the previous page. I'm just wondering, what does N stand for in the formula? That's one of the questions.
So N is number. N is the number. So if N is 50, you could write a formula. So it would be C50, H102. So N is little.
And also on page 161, it says the series that we learned about in fuels are, there's 3 spaces.
So the series are alkanes, alkenes, alkynes.
Okay. Thanks.
And you can put aromatics in that, so because we're going to do them as well. So it's alkanes, alkenes, alkynes. And we're going to look at aromatics. So we're actually doing 4 homologous series. Okay, so if you are happy, you are free. We will see you on Wednesday. Enjoy the lovely day at some point.
Miss,
Yeah.
are we done with the models, or do we send you pictures of them?
You can send me pictures of them. So if you want to stick them at the bottom of your homework, like just take an overall above picture unless you've eaten some. But just, I would like to see, because I might find some errors for you. Also get to eat them, but we do need them on Wednesday, so don't eat them all. Okay. Lovely to see everybody. School
Thanks,
misses
Miss.
school
Thank
misses
you.
you. My room isn't quite the same.
Thank you.
Bye.
Thank you.
Bye.